everyone, and welcome back. My name is Mr. Kowalt, and in this video, we're going to go over how to use stoichiometry and conversion factors to help us determine how long seven astronauts could survive on a shuttle that is cleaning the carbon dioxide out of the air that they are breathing out. So let's get into this. So in this problem, the Space Shuttle Environmental Control System handles excess CO2, which the astronauts are breathing out, and it contributes 4.0% by mass of the exhausted air. So of the exhausted air that the astronauts are breathing out, 4.0% of that is by mass is going to be carbon dioxide. And the system removes the excess CO2 by reacting it with lithium hydroxide pellets to form lithium carbonate and water. So if there are 7 astronauts on board the shuttle and each astronaut exhales 20 liters of air per minute, how long could clean air be generated if there were 25,000 grams of lithium hydroxide pellets available for each shuttle mission? So we're asked here to assume that the density is 0.0010 grams per milliliter. Okay, so how do we begin this problem? So the first thing you want to do is kind of take out all of the conversion factors or underline the conversion factors that you're going to use. So one of the things that you want to pay attention is percentages are conversion factors. So you want to pay attention to percentages. Densities can be used as conversion factors, so that will be useful as well. And we're going to be using stoichiometry because it's asking us, it's telling us that we're given one substance, lithium hydroxide, and they want to know, well, how much time will it take to clean the carbon dioxide out of the air? Basically, we would need to calculate how much carbon dioxide in the air could that amount of lithium hydroxide actually react with. So we need to go from the amount of lithium hydroxide we're given to the amount of carbon dioxide that it could react with, and therefore the amount of air that could be cleaned from that amount of lithium hydroxide. So we're going to have to start with the lithium hydroxide pellets, and then we're going to have to convert our way to the amount of air that is exhaled that then therefore is cleaned by this system. So let's go ahead and do that. So we're going to start with the 25,000 grams. 25,000 grams of lithium. So 25,000 grams of LiOH. Okay. So what we need to help us convert is a balanced equation. And so they tell us that the lithium hydroxide, so we have LiOH pellets, are going to react with the carbon dioxide, CO2 gas, to form the lithium carbonate. Let me give myself some room here. So lithium carbonate, that's Li2CO3. And I believe that's a solid. And water, H2O. So we need to balance the equation. Here I have 1 lithium. I have 2 lithium, so I'm going to have to put a 2 here. Here I have 2 hydrogen, and then I have 2 oxygen here, 2 oxygen there, so that's 4 on this side. I have 3 oxygen plus 1 oxygen, that's 4. So now I have a balanced equation. So now I can use this to help me convert from lithium hydroxide to carbon dioxide. So the first thing I'm going to do is convert to moles, because if I'm going to convert from one thing to a different thing, I need the mole ratio. So I'm going to use the mole ratio of 1 to 2 here, but I need moles. So the first step is to convert to moles using the molar mass. And the molar mass is 23.95. So 23.95 grams of the lithium hydroxide goes on the bottom. And then on the top, excuse me, on the top I have 1 mole of the lithium hydroxide. So grams of the lithium hydroxide cancel out. Now I have moles. Now I can use the mole ratio between lithium hydroxide and carbon dioxide to convert to moles of carbon dioxide. So I'm going to do that. So I have moles of lithium hydroxide on the top. I'm going to put moles on the bottom. So I have 2 moles of the lithium hydroxide on the bottom, 1 mole of carbon dioxide on top, 1 mole of CO2. So now moles of the lithium hydroxide cancel out. Now I have moles of carbon dioxide, but I'm going to have to get that to grams because they're telling me that the air that's exhaled from the astronauts is 4.0% by mass. So this is the carbon dioxide, but that's only 4% of the air that's exhaled. So I want to now convert to the mass of air. So I'm going to have to convert this to grams first. So the molar mass of carbon dioxide is 44.01. So 44.01 grams of CO2 on the top. And then on the bottom, I have 1 mole of CO2. So the moles of CO2 cancel out. Now I have grams. So now I can use the percent by mass. So I know that a percent means out of 100. So how do I use that as a conversion factor? So 4.0% by mass means that out of 100 units of my exhausted air, right, the exhaled air, 4 of those units is going to be carbon dioxide. So out of 100 units, only 4 is carbon dioxide. So the unit we use could be anything. Since I have grams here and we're talking about percent by mass, so then that would mean out of 100 grams of air, 4 grams is going to be the carbon dioxide. So I can use that. So I have grams of carbon dioxide here, so I'm going to put 4.0 grams of CO2 on the bottom, and then 100 grams of the air that's exhausted on top. So grams of the carbon dioxide cancel out. Now I have grams of air, but I want liters of air because they tell me that each astronaut exhales 20 liters of air. So I need to get to volume. So, but here I have mass. So I need a relationship between grams and volume, or mass and volume, and they gave me the density of air. So here they're telling me that the density of air is 0.0010 grams per milliliter. So I can use that to convert to milliliters. So I have, where'd it go? 0.0010 grams. That's going to go on the bottom. 0.0, not 1.0. 0.0010 grams of air on the bottom and 1 milliliter of air on top. So grams of air cancel out. Now I have volume of air, but now I want liters because my unit here is in liters, right over here in liters. So now I got to convert milliliters to liters. Oops. Sorry about that. So I'm going to put 1 milliliter of air on the bottom, and that's equal to 1/1000th, excuse me, 1/1000th or 10 to the negative 3 liters of air. I'm going to put that on top. So milliliters of air cancel out. So now I have liters of air, liters. So now I can calculate the number of liters of air. But before I do that, I need to figure out how many liters of air per minute is produced by the astronauts. And we have 7 astronauts. So if I take the 7 astronauts, I know each astronaut is exhaling 20 liters per minute. So if I take the 20 liters, 20 liters per 1 minute, this is going to give me the amount of liters of carbon liters of air that's exhausted by all 7 astronauts per minute. So right now, this is the amount of liters per minute for 1 astronaut. But if I multiply by 7 astronauts, that's going to give me the total amount from all astronauts that's exhaled. So, oops. So when I multiply this, that gives me 140 liters per minute exhaled. So with all 7 astronauts, 140 liters of air is going to be exhaled per minute. So now I can use this to convert the liters of air that I have into time in minutes. So then I'm going to continue this down here. So I'll continue down here. So I have here. So I have liters of air on the top. So I'm going to put 140 liters of air on the bottom. And I'm going to put 1 minute on top. So, oops, that should be liters of air. So liters of air are going to cancel out here. And now I got minutes, but the minutes isn't really going to be a good measure of the time that the astronauts are out there or the time it takes to clean the air. So I'm going to convert this to days. So I know, first I'm going to convert to hours. So I know that there are 60 minutes in 1 hour. So minutes cancel out. And now I can convert to days. So 1 hour. So hours are going to go on the bottom. So I know there are 24 hours in 1 day. So hours cancels out. And now I have days. So now I can calculate the number of days that this amount, that 25,000 grams of lithium hydroxide, can clean or generate clean air. So when I calculate this out, I get 2.84 and some change days. So that's the number of days. I have to pay attention to significant figures. Remember, when you're multiplying and dividing, your answer should have the same number of sig figs as the least number of sig figs in the measurements you're multiplying and dividing. So let's take a look. So here I have 2 sig figs. Here I have 4 sig figs. This is exact. Here I have 4 sig figs. Here I have 2 sig figs. Here I have 2 sig figs. This is exact. This is 2 sig figs. This is exact. This is exact. So the least number of significant figures is 2. So that means that I should only have 2 sig figs in my answer. So 1, 2, cut it off after the 8. This is a 4, so this is going to stay at 2.8. So 2.8 days is the amount of time that 25,000 grams of lithium hydroxide can generate clean air. I hope this is helpful. If you enjoyed this video, if you learned anything from this video, then please, by all means, like the video, share the video, hit that like button somewhere over here. Also, make sure that you subscribe to my channel. Help me out here. Also, click that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to help you with that. If you have any questions or problems you need help with, if you have a topic you want me to cover, write that down below. Thanks for joining me and have a great day.